Hello guys, and welcome to another video. So in this video we'll be answering these set of questions, and the first instruction here says write down the two models that are used to explain the behavior of electromagnetic radiation. And the answer, guys, is that electromagnetic radiation behaves as a wave model or as a particle model. That's our answer. So it's going to behave like a wave or rather and a particle model. That's how it behaves. And then 6.2 says identify the type of electromagnetic radiation that has the longest wavelength. Okay. All right, guys, from Ronaldo's mother is visiting Uncle Xavier's garden. We know that the radio waves are the ones that are going to have the longest wavelength. And then which ones are used to detect fractured bones? It is going to be the x-rays, guys. That's what will work. The x-rays can scan through bones. So that's going to be our answer for 6.2.2. The ones with the longest wavelength, radio waves, the ones used to detect fractured bones are going to be the x-rays. Okay, guys, and this is how you're gonna mark your work. 2 marks here, 1 for each model, and then 1 mark for each answer here. Now we move on to the next question. Okay, guys, now we are in the next part of our question, and here it says the graph below, not drawn to scale, shows the relationship between wavelength and energy of a photon light, is of a photon of light. And before we just go into this graph, guys, we will remember that the relationship between energy and the wavelength is actually supposed to be inversely proportional, and this graph shows that relationship. It shows an inverse proportion relationship between energy and wavelength. That means if we have a high energy, we will have the low, or rather the short short wavelength. Okay, then to our set of questions, the first question here, 6.3.1, says define the term photon in words. And how do we answer that question, guys? We say that a photon is a packet of energy found in light. Packets of energy found in light, or rather packet of energy found in light. Then 6.3.2 says what is the mathematical relationship between wavelength and energy of its photon? And we just talked about it, guys. We are gonna say the relationship is inversely proportional. Okay, inversely proportional. 6.3.3 says calculate the wavelength of a photon at point A on the graph. So if we look at our graph, guys, the y-axis shows us the values of the energies, and the x-axis shows us the values of the wavelength. So if they say we must find the wavelength of a photon at point A, this is where point A is. Let me just use it different. Let me highlight it like this. In fact, this is where point A is. So we are going to work with this energy here, the 2,6. And this 2,6 is supposed to be 2,6 times 10 to the power of negative 14. Okay, so that's the energy we are using. And the formula we are working with is what? Is the one that has wavelength. Okay, it's the one that has what? It's the one that has wavelength. And that formula is E is equal to hc over lambda. Let's write it down. So this is our formula, and now we are going to substitute. What is our energy? Our energy is going to be 2,6 times 10 to the power of negative 14. 2,6 times 10 to the power of negative 14 is equal to our Planck's constant. We know it is 6,63 times 10 to the power of negative 34. And our c is what? The speed of light, which is 3 times 10 to the power of 8 divided by our lambda. It's what we are looking for. We say this energy is divided by 1. then we cross multiply. What we are gonna see is this lambda multiplied by 2,6 times 10 to the power of negative 14, and we are going to get 2,6 times 10 to the power of negative 14 lambda is equal to, and we are now going to multiply this one and this one, then we'll put that on the calculator. So we are saying this one multiply by this one. So on the calculator I put in this as it is. Okay, let's do that. And when I say Planck's constant times speed of light, the answer I'm getting is, sorry about that, the answer I'm getting is 1,989 times 10 to the power of negative 25, and then I will obviously now divide by 2,6 times 10 to the power of negative 14 on both sides. 2,6 times 10 to the power of negative 14. We know that this side they are going to cancel, and then what I'm going to do is take all of this and put it on the calculator exactly the way it is. So I'm gonna say this divided by that on the calculator, and that means, guys, excuse me, that means that my wavelength is going to be equal to, when I say this number divided by this one, the answer I'm getting is 7,65 times 10 to the power of negative 12. And what is the unit for wavelength? It's going to be meters, and that's how you answer that question. Then we go to 6.3.4. They say here, determine the frequency of a photon at point B on the graph. So if we look at point B on the graph, this is where point B is on the graph. Point B is over there, and it has a relationship with this energy now. So we will use this energy to find our frequency. And which formula are we going to use, guys? We are going to use E is equal to HF, because we are looking for frequency. Okay. Before we go to that next question, I just thought I should show you how you mark. You should give yourselves 2 marks for the definition. Give yourself 1 mark for saying inversely proportional. Then for 6.3.3, you're going to give yourself a mark for the formula, then the substitution of energy, and then the substitution of the Planck's constant and speed of light, and finally the answer. Now let's look at 6.3.4. So this is the formula we are using for 6.3.4. Obviously, there'll be a mark for that. And then we check the energy that is related to B, and that energy is going to be what? It's going to be 1,59 times 10 to the power of negative 14. Where am I getting the times 10 to the power of negative 14? I'm getting it here. Okay, so that's what we are going to have there. We'll have, okay, I forgot the value. It's 1,59 for the energy. 1,59 times 10 to the power of negative 14 is equal to, do I know my Planck's constant? Yes, I do. My Planck's constant is 6,63 times 10 to the power of negative 34, and it's multiplied by F. Because I'm looking for F, it means I have to divide by the coefficient of F, which is the Planck's constant, that is 6,63 times 10 to the power of negative 34. And I should do this on the other side as well. 6,63 times 10 to the power of negative 34. These are going to cancel. Therefore, my frequency is what? I'm going to take this exactly as it is, put it on the calculator, and find my answer. And yeah, when we press our calculator, guys, the answer that I'm getting is 2,40 times 10 to the power of 19. And what am I going to write as my unit? I'm going to write hertz. And then that will be it. I'll show you how to mark there. So for this one, you mark the formula, you mark the substitution everywhere, and you mark the final answer. Let me just confirm if it's 3 marks. Yes, it is. So that's how you mark. Now we go to question 6.3.5, and it says, at which point, A or B, will a photon have greater penetrating ability? Give a reason for the answer. Okay, let's go to that part there. So here they're asking, at which point, A or B, will a photon have greater penetrating ability? Again, we have to remember that, guys, penetrating ability is directly proportional to energy. The more energy we have, the greater the penetrating ability. So the answer we are going to give here is to compare the energy at point E, at point B, and the energy at point A. But we see that the energy at point A is actually larger than the energy at point B. So our answer then for 6.3.5, our answer for this question is going to be A. And why are we going to say A? It's because A has the highest energy. Okay, so guys, we are going to say A, and our answer, or rather reason, is because A has the highest energy than B. Hence, it has the greater penetrating ability. And this is how you mark for A. Then you mark where you compare the energies, that A has the greater energy than B. Then you'll mark your conclusion that this is why A has the greater penetrating ability. So it's gonna be 3 marks like that. And that concludes the corrections or us going through this question. I'll see you on the next one. Enjoy. Bye bye.